Welcome to qnawire.
You can apply the angular momentum. You can apply the concept of angular momentum to the Earth meteorite system before and after the collision. So we can say that the initial angular momentum equals the final angular momentum, and this would be equal to the moment of inertia for the Earth multiplied by the initial angular velocity minus the mass of the meteor times the mass of the Earth, my apologies, times the radius of the Earth times v sine 45 degrees. And then this would be equaling the moment of inertia for the Earth plus the moment of inertia for the meteorite multiplied by the final angular velocity. And so we can say that the final angular velocity would be equaling the moment of inertia for the Earth times the initial angular velocity minus the mass of the Earth times the radius of the Earth, v sine of 45 degrees. This is going to be divided by the moment of inertia for the Earth plus the moment of inertia for the meteorite. This would be equaling, we can model the Earth as a sphere, and this would be 2/5 times the mass of the Earth, radius of the Earth, squared times the initial angular velocity minus m r sub e v sine of 45 degrees. And so we can then, this would be divided by 2/5 times m sub e r sub e squared plus m r sub e squared. I said that lowercase m was mass of the mass of the Earth. My apologies. Lowercase m is actually going to be the mass of the meteorite. My apologies. Because initially we have to account for the mass of the meteorite because it is also going at a linear speed towards Earth. So my apologies. Lowercase m is indeed the mass of the meteorite. And so we can say then that omega final over omega initial would be equaling, this would be 2/5 times the mass of the Earth, radius of the Earth, squared minus the mass of the meteorite times the radius of the Earth, multiplied by the initial, or rather the linear velocity of the meteorite divided by the initial angular velocity, multiplied by 1 over radical 2, and then this would be divided by the radius of the Earth squared multiplied by 2/5 times the mass of the Earth plus the mass of the meteorite. And so we can say that the final angular velocity divided by the initial angular velocity would be equaling the radius of the Earth squared multiplied by 2/5 times the mass of the Earth minus the mass of the meteorite times the linear speed over radical 2 omega initial r sub e. And then this entire term would be divided by the radius of the Earth squared multiplied by m plus 2/5 times the mass of the Earth. Of course, these are going to, the radius of the Earth squared term is going to cancel out for both the numerator and the denominator. And so we can then say that here the change in the angular velocity divided by the initial angular velocity, this would be equaling the final angular velocity minus the initial angular velocity over the initial angular velocity, and this would equal the final angular velocity divided by the initial angular velocity minus 1. And so we can say that the change in the angular velocity divided by the initial angular velocity would be equaling 2/5 times the mass of the Earth minus mv over radical 2 times the initial angular velocity times the radius of the Earth. And then this term would be divided by the mass of meteorite plus 2/5 times the mass of the Earth minus 1. And so this would be equal to negative This would be negative v over radical 2 times the initial angular velocity times the radius of the Earth plus 1, and then divided by 1 plus 2/5 times the mass of the Earth divided by the mass of the meteorite. And at this point, we can solve. So delta omega over omega initial, this is going to equal, this is going to be quite large. So for the numerator, we have 2.2 times 10 to the 4th meters per second. This would be divided by radical 2 multiplied by 2 pi over 86,400 seconds, or 1 day, radians per second. This would be multiplied by the radius of the Earth, 6.38 times 10 to the 6th meters. And then this would be plus 1. And then this would be divided by 1 plus 2/5 multiplied by the mass of the Earth, 5.97 times 10 to the 24th kilograms, divided by the mass of the meteorite, 5.8 times 10 to the 10th kilograms. And so we find that the change in the angular velocity with respect to the initial, or rather over the initial velocity, would be equaling negative 8.39 times 10 to the negative 13th, and this would be our ratio. That is the answer. Thank you for